Thermochemistry Extra Practice example number 8. So to build these, I taught you that you're just going to connect these. We're going to figure out how to build all of these. And because we're looking at individual bond energies, so we're looking at how bonds are broken. So this is the sum of the bonds broken minus the sum of the bonds formed. This is the only time all year that we've put reactants minus products. We're going to use the sheet that has the different energies for every types of bond, and we're going to have to establish the types of bond in each piece. So here we're going to make this thing, we're going to connect, remember, the carbons all together. There's 7 of them. 1, 2, 3, 4, 5, 6, 7. We connect them in what we call a continuous chain. 1, 2, 3, 4, 5, 6, 7. We have 13 hydrogens to attach. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then we have an OH to attach. Remember, OH is going to be attached as this, which is really this. Okay? Now, here's the problem. Every carbon must have octet. Actually, every element must have octet in here except for hydrogen. There are others, but in this example, everything has octet. There are 3 examples that don't have octet. By the way, octet means 8 electrons. So hydrogen, boron, and beryllium are the exceptions to octet. Okay, so hydrogen doesn't have to have 8 electrons attached to it, but everything else does. Remember that every stick counts as 2. So this carbon has 2, 4, 6, 8. This carbon has 2, 4, 6, 8. This carbon has 2, 4, 6, 8. Remember, every stick counts as 2. There are hydrogens on the end of these sticks. I'm just not writing them out. And then this carbon has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Remember, these are all hydrogens here. That might be a better visual for you. Let me put them in really quick. A little sloppy, but you get the idea. And then I attach the... Here's the problem. This carbon does not have octet. So there's something wrong with that structure, and I have no more hydrogens to give. If you count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, plus the OH, I have nothing else I can add to this. If that is the case, then that means you have to put in a double bond, or multiple double bonds, or a triple bond. So we're going to try first putting in a single double bond, put in 1 double bond in the beginning, and then do your 7 carbons, the rest of them with the single. So 1, 2, 3, 4, 5, 6, 7. Okay, and I'm going to, I'm going to move that. Let me move this, let me erase this and move this down. And let me get rid of some of this so that I have room to show you. I need room to put my hydrogen. So I said you're going to do a double bond. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Give octet again. This has 1, 2, 3, 4. So these are hydrogens. And then this is a hydrogen. That's 5. That has 8. 2, 4, 6, 8. Remember, hydrogen doesn't need 8, but carbon does. Everything in here except hydrogen needs 8. This has 2, 4, 6, 8. Every stick counts as 2. This carbon 2, 4, 6, 8. 2, 4, 6, 8. Let's see where we're at. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then this is, remember, really this. Okay, we attach it like this, but it really is an C goes to the oxygen. The carbon is attached to the oxygen, but the oxygen is attached to a hydrogen. So let's see if we have our 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And we have our OH attached. So now everything in this piece is attached. Let's see if we have octet for all the carbons. 2, 4, 6, 8. This carbon, 2, 4, 6, 8. This carbon here. Third carbon, 2, 4, 6, 8. Fourth carbon, 2, 4, 6, 8. This carbon, 2, 4, 6, 8. This carbon, 2, 4, 6, 8. This carbon, 2, 4, 6, 8. And this oxygen, you don't know this, but it's going to have this. It doesn't matter for what we're doing. And that would have been true up here also, because then that oxygen would have had 2, 4, 6, 8. But you can just attach it as a unit. And so now we have what we need. We have that structure drawn. So that's going to be our first structure. I'm going to show you that in a very much neater way in just a moment, but I wanted to show you how you get there. Now we're going to work next with this piece here. So I'm going to clear my screen and work with that piece. And I'll put these pieces together in a minute so that you don't have to write anything down. You're just understanding in the process here. So oxygen has to have 8, so we connect them with a single stick and give them octet. So we always connect everything with a single stick and then give everybody octet except for hydrogen. 2, 4, 6, 8. 10, 12, 14. Now here's the thing with oxygen. I didn't do the count with here because this count status can be done, but I think it's more confusing to do that. So let me talk to you about the count status on this, and then we'll go back and look at that. So let's actually go back for just a moment and look at that count status. I should have done that first, or the total electrons we can have. Okay, so we know that this is this is not the proper structure because we didn't have things. We know this is the proper structure. Over here is where I'm showing you how we calculated the magic number, I like to call 48, meaning that I can figure out how many electrons a structure must have based on a few pieces of information. So I look at the structure, in this case C7, H14, so 13 H's plus this, that's how I get the H14 in oxygen. I look at the valence electrons, that's the family number. Carbon is in family 4A on the periodic table, so it has 4 valence electrons. Hydrogen is in family 1A, so it has 1 valence electron. And oxygen is in family 6, so it has 6 valence electrons. That would be the heading at the top of the periodic table where the element is found in the column. The top of the column either has Roman numerals A's and B's, or it has 1 through 18. So you're going to look at the Roman numeral. If you look in the carbon family on a periodic table, you'll see there's a 4A at the top of its column. Hydrogen has a 1A at the top of its column on the periodic table, and oxygen has a 6A. So I take the numbers of carbons, 7 in this case, times 4 is 28. I remember I have 14, 13 plus 1, so 14 total hydrogens times 1 is 14, and 1 oxygen times family 6 is 6, and I get 48. Now we're going to see if our object, our structure, I should say, has a total of 48 electrons. There's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. So that has the right structure. I find it difficult to do this with something like this rather than the process I initially showed you, but I wanted to show you how you get the number of electrons you need in a structure. So now let's go back to this piece and look at this piece only. So we know we have oxygen. There are 2 of them. It's in family 6, so I get 12 electrons total. So I'm going to attach them with a stick and give everybody octet, because remember, only ones that don't get octet are hydrogen. So those each have 8, 2, 4, 6, 8. I first connected them with the stick. That counts as 2. So this oxygen here is 2, 4, 6, 8. This oxygen has here 2, 4, 6, 8. Yes, I count the stick to both left and right side. So let's see if we have our 12. 2, 4, 6, 8, 10, 12, 14. 2, 4, 6, 8, 10, 12, 14. So 14 is too many. So now we're going to put in a double bond like we did a moment ago with the carbon piece, and then give octet again. So this oxygen has 2, 4. Those sticks count each as 2. So we have, that's 6, that's 8. This oxygen has 2, 4, 6, 8. Now I haven't emphasized this, but remember that we need to do octet before we look for this number. So you need to get octet done on everybody except for hydrogen before we get this number. So now 2, 4, 6, 8, 10, 12. So this is the correct structure for oxygen. These electrons pairs that are there are not necessary to be able to do this problem, but they are there to show that they are physically there to show the octet rule and to get to our number. So your choice is to know how to do this, right? Know how to do this, or memorize that oxygen is always an oxygen double bonded to oxygen. So an O2 is always going to be oxygen double bonded to oxygen. Now let's look at the CO2 situation. So we have C and we have O. We have 1 C, we have 2 O's. This is in family 4. This is in family 6. So 4, 12. So we have 16. So we're going to attach each of the oxygens to the carbon. How do I know that's the case? Because I have not said this yet, but the first atom is central unless it's hydrogen. So the first atom you come to is in the center unless it's hydrogen. So I put carbon in the center because it's first, and I attach a hydrogen on each side. Doesn't really matter where you attach them, left, right, top, bottom. Now we're going to give everybody octet. That's 2, 3, 4, 5, 6, 7, 8. This carbon has 2, 4, 5, 6, 7, 8. This oxygen has 2, 3, 4, 5, 6, 7, 8. Remember, I'm trying to get 16. Everybody has octet. Now I'm going to try to get the 16. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So that's not the right structure. So now we're going to put in a double bond and go back and give everybody octet. This oxygen has 2, 4, 6, 8. This carbon has 2, 4, 6, 7, 8. This oxygen has 2, 3, 4, 5, 6, 7, 8. 2, 4, 6, 8, 10, 12, 14, 16, 18. So still too many. So now I'm going to try a set of double bonds. This carbon, so now we're going to do octet. We always do octet before we check our magic number. This oxygen has 2, 4, 5, 6, 7, 8. This carbon has 2, 4, 6, 8, so it gets no more dots. This oxygen has 2, 4, 5, 6, 7, 8. Now that we've checked, we know that didn't work and that didn't work. Now that we know everybody has octet, then we check to see if we get the magic number of 16 that we have here. 2, 4, 6, 8, 10, 12, 14, 16. So we know that carbon dioxide is going to be O, double bond carbon, double bond O. Oxygen, double bonded carbon, double bonded oxygen. You can either understand this process here, or you can memorize that carbon dioxide will always be oxygen, double bonded carbon, double bonded oxygen. Let's do the last one. Let's do water next. So here we have H, and we have 2, we have O, and we have 1. Hydrogens in family 1, oxygens in family 6. So we have 2 plus 6, which is 8. Now remember I said the first atom is central or in the middle unless it's hydrogen. So hydrogen's first, so that means oxygen's in the middle. Remember that hydrogen does not have octet, but oxygen needs it. So hydrogen would get whatever it lands on. Usually it's, well, it is not usually it's 2. A hydrogen only has 2, but you don't need to memorize that. Just know it doesn't have octet. So here we're going to see if we have 8. Once we establish everybody that gets octet has it. Hydrogen doesn't get octet, but oxygen does. So 2, 4, 6, 8, it has it. And then I count and I have 8. So you can either memorize this process or memorize that water is going to be H, single bond oxygen, single bond hydrogen. So hydrogen, single bond oxygen, single bond hydrogen. Again, you can either memorize these 3 as oxygen is this, carbon dioxide is going to be this deal, and hydrogen is going to be this deal. Or you can understand the process of how to get there. It's up to you. Now, all of that is first year chemistry stuff. Now I'm going to show you how to apply it to here. So I drew all those out in the video that we just did, and here is an electronic version of that. So this is the drawing, or very close to the same drawing I drew a moment ago. We know oxygen is O, double bond oxygen, double bond oxygen. This is oxygen, double bond carbon, double bond oxygen, and water is hydrogen, single bond oxygen, single bond hydrogen. I know that there are lone dots on some of this stuff, but we don't need those for what we're about to do. All right, the next piece is that you're going to evaluate what each structure has in it. And we're going to do that next. Okay, the next step is that we're going to evaluate the types of bonds, because we're using bond energies to do this. So we see here that we have carbon double bonded to carbon, and we have carbon single bond to carbon in that structure. We have carbons bonded to hydrogens, carbons bonded to oxygens, and hydrogens bonded to oxygens. Okay, so if you look at here, we have, this is a carbon bonded to a carbon. This is an example of a carbon bonded to a carbon, carbon bonded to hydrogen, carbon bonded to oxygen. And remember, this was an oxygen bonded to hydrogen. So now we're going to count. We have 1 carbon-carbon double bond. Count the bonds. We have 1, 2, or count the sticks. So 1, 2, 3, 4, 5 carbon-carbon single bonds. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 carbon hydrogen bonds. We have 1 carbon oxygen bond, and we have 1 we have 1 hydrogen oxygen bond. So 1 carbon oxygen bond right here, and then 1 hydrogen oxygen or oxygen hydrogen. Now we're going to get the bond energy numbers off of the table that has them. You are given that table. It's on the back of your formula page in your assessment. So when I look up the bond energy values for a carbon-carbon double bond, I get 602. For a carbon-carbon single bond, I get 346. For a carbon-hydrogen bond, I get 411. For a carbon-oxygen bond, I get 358. And for oxygen-hydrogen bond, I get 459. If there would have been a number in here, out in front of here, I would have had to multiply this final answer by that number. Okay, so we're going to do this. We're going to do the math here. We get 602. We get 1730. We get 5343. We get 358. We get 459. And now we're going to total those. So we're going to add those up, and it's 8492. So that's just that first structure. And is there a multiplier in front of it? There is no number here, so there's no multiplier. It's going to stay 8492. Okay, on this next piece, we know that this is an oxygen. This has oxygen-oxygen single bonds, and there's 1. In this piece, there's 1 oxygen oxygen, double bond. Oxygen double bond, I meant to say. I'm not sure what I said a moment ago. As I look on my sheet, I see that an oxygen double bond is 494. So that's 494. But I have a multiplier of 10, or I have 10 of those, so I got to multiply that by 10. So I get 4940. Okay. Going on to this next piece. Here I see that I have carbon double bonded oxygens, and I have 2 in the structure. And that's going to be a value of 799. And we're going to, that is 1598. But this multiplier, or the coefficient, means I have to multiply that by 7. When I do that, I get 11186. Okay, and then I have hydrogen, oxygen in water, and I have a hydrogen oxygen bond, and in every water I have 2 of them. And a hydrogen oxygen bond is 459. So we're going to take 459 times 2, and we get 918. 918, but the multiplier in front is a 7 right here, because we know every water is going to be 918, but there's 7 of them in the balanced equation. That is going to give us 6426. Okay, so now what we're going to do is we're going to calculate bond energies. Remember, in the beginning of this set of notes, I said it's going to be the sum of the reactants minus the sum of the products, or bonds broken minus bonds formed. Okay, so that is where we're going to think about this, as this is how we divided it. So we're going to take the 8492 plus the 4940. Actually, let me go ahead and just, instead of doing it this way, let me get out and I'll type it out for you. It'll be easier to do that. Let's do that. So we're going to take the reactant side, which is 8492 plus 4940. That's the reactant side. Minus the product side. That's going to be 11186 plus the 6426. Let me just expand this on top of things just so you can see it. See if we can make that red. Maybe that'll... So that is the work from the reactant side. So this was a reactant, 8492. This is the other reactant, 4940. Product, 11186 and 6426. So this is the reactant side and the product side. And now we're going to sum these, sum this side, and subtract the 2. Let's go through and do that. So we're going to take this. I'm trying to find a spot on the screen. So we're going to take 8492 plus 4940, and that's going to be 13432. So that is going to be 13432 minus, let me bring up my calculator, make sure I have that written correctly. Let's try that again. So that was 8492 plus 4940. Let's try that again. I did not do that correctly. Apologize for that. 8492 plus 4940. 1342, so I agree with that side. And now let's do the other side. 11186 plus 6426 equals 17612. And let's verify that one more time. 17612. Oops. All right, so then let's go through that and do that piece. Let's clear this out. We got 13432 minus 17612. And we get total to be negative check that again. 13432 minus 17612, and I get negative 4180. Kilojoules per mole. That would be your final answer. What do? We took the sum of the reactants minus the sum of the products. This was the sum of the reactants. This was the sum of the products. We subtracted the two, and this would be our final answer. So the final answer is negative 4180 kilojoules, technically kilojoules per mole.